G'day, thanks for joining me on our first lesson into Unit 6 entitled Electrochemistry. We're starting this unit by looking at redox processes, half equations, and oxidation states, where our lesson objective is to understand and explain redox reactions in terms of electron transfer and oxidation numbers. The two learning outcomes from the Cambridge curriculum we're looking at this lesson. So as you might be able to infer from the name of the unit, electrochemistry, this is sort of revolved around electricity and the electron, where electricity is really just a flow of electrons from one point to another point. So what we're looking at in the electrochemistry unit is the transfer of electrons, so how electrons are moving within chemical reactions. So some of the chemical reactions we're going to see look a little bit different to what we've looked at previously, but we're all going to cover everything quite in depth and we'll be going on, no worries. So let's look at this redox reactions. This is a type of reaction that we have not looked at. A type of chemical reaction where one species undergoes reduction and the other species undergoes oxidation simultaneously. As you might be able to infer from this name, oxidation, traditionally it was used to describe a reaction where a species gains or loses oxygen. And it's still used to describe those kinds of reactions. In fact, oxidation and reduction can be used in a few different situations to explain a few different types of reactions that we're going to look at in just a second. But oxidation, if something's being oxidized, it is gaining oxygen. If it's being reduced, the oxygen is being reduced off it, so it's losing oxygen. So that's where the name oxidation and reduction comes from. For example, we have a chemical reaction here. Aluminium is reacting with oxygen to form aluminium oxide. The aluminium is gaining oxygen, so the aluminium is being oxidized. This is an oxidation reaction. An example of a reduction reaction using this definition, we have iron oxide being turned into iron. It's being reduced, it's losing that oxygen. It also describes the addition of hydrogen, so a reaction that involves adding hydrogen would be called a reduction, or removing hydrogen would be called oxidation. More generally though, and more specific to this unit where I just said it's looking at how electrons move, it can be used to describe how the electrons being transferred between two different species. So it describes reactions involving the transfer of electrons. Where redox is a portmanteau of reduction and oxidation. Portmanteau is where you've got one word and another word and you sort of smush them together to have elements of both words. Like brunch is breakfast and lunch. Reduction, oxidation, smush them together, portmanteau, you get redox. And there is a useful acronym, oil rig. We like an acronym every now and then. You can remember easily what is happening for the transfer of electrons because oxidation is the loss of electrons, reduction is the gain of electrons. And this forms the acronym oil rig that we can easily remember. Oxidation is loss, reduction is gain. So all these three descriptions in terms of gaining or losing oxygen, gaining or losing hydrogen, or gaining or losing electrons, they all describe three different things, but they're all the same type of reaction essentially. So if we looked at the species being oxidized and reduced up here when we're gaining and losing oxygen, they're also fulfilling this definition down here with the idea of gaining or losing electrons. So redox reactions, reduction, oxidation occurring simultaneously. Oxidation is a species that's losing electrons, reduction is the species that is gaining electrons. And we can look at the electron transfer or changes in oxidation numbers to determine if a redox reaction has occurred. That will make more sense in just a moment. So we're going to introduce this idea of half equations, which are equations that we haven't really seen before in this course. Let's consider the oxidation of magnesium when we are going by that idea that it's just gaining oxygen. So if we got magnesium solid, and if I do a combustion reaction where I react that with oxygen, if you burn a magnesium strip over a Bunsen burner in the presence of oxygen, you get a really, really bright, it's a very exothermic reaction. It lets off UV light, so you can't look directly at it, but it's quite a brilliant sort of amount of light and intensity of light that's given off. This will form an ionic compound, magnesium oxide, and you can see this will be the sort of the white material that's left that sort of coats itself on the cover of over the top of the magnesium ribbon that you just burnt. We've got to make sure this is balanced like that. So this is an oxidation reaction where magnesium is reacting with oxygen to have an oxidized substance essentially. Rightio, so let's consider how the electrons are transferring here when we talk about the idea that oxidation is loss of electrons and electron is gain of electrons. If we draw a magnesium atom, I got magnesium there, and I have 2 electrons in the valence shell, 1, 2. Over here, we are forming an ionic compound. So we have Mg2 plus and O2 minus. So essentially, what's happening is the magnesium is losing its 2 electrons to the 2 oxygen atoms. So we have oxygen as a covalent compound, but if it was to break that oxygen double bond oxygen there, and we just had the oxygens with their 1, 2, 3, 4, 5, 6 electrons there for that atom, and the 1, 2, 3, 4, 5, 6 there for that atom. This is a bit of a simplification, but it illustrates quite easily what I'm trying to say here. Magnesium is giving an electron over there. Magnesium is giving an electron over there. But we've got 2 magnesiums, so I need to have a second magnesium atom. So second magnesium atom down there with 1, 2. And we're given 2 electrons. I don't know why I crossed over like this. But we can see that this magnesiums here, they are losing the electrons, and the oxygens over here are gaining the electrons. So the magnesium species is being oxidized because it's being reacted with oxygen, but it's also being oxidized in the terms of the electron transfer. Oxidation is loss of electrons. So consequently, the species that is not getting oxidized needs to be getting reduced. So this species here is gaining the electrons, and we end up with our ionic compound over here. So we got magnesium 2 plus with the oxygen 2 minus. And we've got 2 of those. Magnesium 2 plus, oxygen 2 minus. So we've got the formation of the ionic bond, and we can see pretty easily which way the electrons are moving, the transfer of the electrons. Again, that's what this study of electricity and chemistry really is, just sort of how the electrons are being transferred. You can see when magnesium is oxidized, it loses electrons. So over here, our magnesium is losing the electrons. And conversely, we can see that the oxidation gains these electrons and is consequently reduced. So a redox reaction, in order for a redox reaction to occur, one species needs to be oxidized and there needs to be another species that is being reduced. Because we have the conservation of mass in everything we do. We can't create or destroy matter. If one species is losing the electrons, then the other species needs to be gaining those electrons because those electrons have to go somewhere. So that's why the redox reaction needs to have the reduction and the oxidation occurring simultaneously. And we can write half equations that show each of these processes. Need to consider the conservation of mass and also the conservation of charge. So if I go back to my whiteboard over here, and if I erase this and we look at this a little bit differently, a little bit clearly, but more importantly, a little bit easier to write. You know, we're busy chemists, we got things to do, we can't be drawing pictures all day. Let's just do some half equations to show what we just had there. So we said that the magnesium is losing the electrons. The magnesium is undergoing oxidation. That's my shorthand for oxidation, OX with a little superscript N. So we have a magnesium. And if we look at the magnesium over here, this is a magnesium ion, a 2 plus ion. I was showing just before my magnesium atoms losing those 2 electrons. So we're going from a magnesium and it's losing those 2 electrons to form a magnesium ion, the magnesium ion being the magnesium ion and magnesium oxide. However, we have the conservation of mass and we've also got what's now called the conservation of charge. So we've looked at lots of these conservations: conservation of mass, conservation of energy, conservation of charge says the same thing. Charge can't be created or destroyed. The amount of charge before the chemical reaction needs to be the same amount of charge that there is after the chemical reaction. So if I look at the charge on my product side of the reaction, I have a 2 plus charge here, but on my reactants over here, I have a no charge. So I've essentially created 2 plus charge and that doesn't balance. And where that other charge is going off to are the 2 electrons that are being lost. So now we can see we're balancing both mass and charge. I've got one magnesium atom going to one magnesium atom. I have a neutral charge over here. I have a 2 plus and a 2 minus, which gives me a neutral charge over here. Conservation of mass and conservation of charge. And I'm showing my oxidation reaction because I'm showing oxidation is loss of electrons. I'm showing my magnesium losing the electrons via a chemical reaction. Some things that we haven't seen in these types of half reactions before is the appearance of an electron in the actual equation itself. Electron in an equation is just given E minus like that. Electron doesn't have a state. Electron's one of our elementary particles. Electron just is an electron, just a sort of point charge. We did a big deep dive on what the electron is a few videos ago, so you can go back there if you want to have a recap on that. But in our chemical reactions, unlike our atoms, we don't need to have a symbol. The electron is just the electron. Rightio, so let's have a look at our reduction reaction that we have here. Remember our oil rig, oxidation is loss, reduction is gain of electrons. And what's gaining the electrons is the O2. So I've started with the O2 in the gaseous state, and what I'm forming is an O2 minus in the solid, in this ionic compound. So what I need to have here, first of all, is the conservation of mass. I've got one O2 molecule here. I need 2 oxygen atoms there. And I mean, that makes sense. If you draw out an oxygen molecule, and then if we're severing that covalent bond to have 2 oxygen ions, well, we need 2 of these to have the conservation of mass, to make sure that the mass is being conserved. Now, we also need the conservation of charge. I have a neutral over on the left-hand side, but I have lots of 2 minuses, so I have a 4 minus over here. So like we showed the electrons being lost up here, I need to show the electrons being gained over here. So I've got my oxygen gas, and I'm plussing the electrons to it to form the reduced species. However, this doesn't balance with the charge yet because I've only got 1 minus over here, but I've got a 4 minus over there. So I need 4 electrons like that. So these are half equations. We're showing the oxidation half equation, we're showing the reduction half equation, and we're showing how these electrons are being transferred between the species. Let's have a looky loo what I got on my slides here. Cool, so that's that one. And that is that one. So the oxidation, the loss of the electrons, reduction, the gain of the electrons. Atoms and charge both need to be balanced in half equations. Okay, so we've got these half equations. Now what we can do is we can combine them to have full equations, full chemical equations. And we've got this new type of chemical equation that we haven't looked at called ionic equations, which, as you might guess, has ions in it. If it's called an ionic equation, it's going to have ions in there somewhere. Soluble substances can dissolve into water and dissociate into ions. We've looked at that previously. Ionic equations, usually for reactions that occur in solution, show how the ions are reacting. Can balance half equations to get balanced ionic equations. In a redox reaction, the electrons gained in the reduction are from the electrons lost in the oxidation. Therefore, the number of electrons lost and gained in a redox reaction must be equal. So I keep harping on about this idea of conservation of mass. You can't create matter, you can't just destroy matter, you can't just pull matter out of anywhere, it's got to come from somewhere. So in our redox reactions where we said we've got a reduction and an oxidation occurring simultaneously, we've got one species losing electrons simultaneously as another species gains electrons. Well, the electrons from the species that's being lost are the electrons that are gained by the species that's getting them, that's being reduced. So if I look over here, the electrons that are coming from the oxidation when it loses them are these electrons that are coming to the oxygen when it gains them. However, this needs to be balanced as well. So if I wanted to do an overall ionic equation for this, what we need to do is to make sure that the electrons are balanced. So if this oxidation reaction only generates 2 electrons being lost, but this reduction reaction needs 4 electrons to occur, that means I've got to multiply this whole reaction by 2. I need this reaction to occur twice for every 1 time that this reaction occurs. So if I do this, it means I've got 2 Mg going to 2 Mg ions and 4 electrons. Now what you might have noticed is that this is the first time we've ever seen electrons in a chemical equation. So if we're doing an overall reaction, we don't want the electrons to be present at all. So we've got to make sure that they cancel out to make sure that mass is being conserved and to make sure that we have a proper full ionic overall equation. So now we can just simply add these two equations together essentially. So if I've got 4 electrons on this side and I've got 4 electrons on that side, they're just going to cancel out. And then my overall ionic equation is going to be 2 Mg solid plus O2. I've only got one of those, O2 gas, and that's going to go to 2 Mg2 plus in the solid plus 2 O2 minus in the solid, which is the same as the equation I've written up there, only I've written it as an ionic equation because I'm showing the ions. So we can make the electrons balance out to make sure we've conserved mass, and then we can get a full combined overall equation for 2 half equations. Let's see what I got in this yellow box. All right, question. Let's do an example. In a redox reaction, nickel is oxidized to nickel 2+, whilst iron 3+ is reduced to iron 2+. Determine the overall balanced ionic equation for this reaction. So we've got 2 half equations. We've got an oxidation reaction and a reduction reaction. So let's write those 2 out. Let me start with my oxidation reaction. As we always say, if you want to pause now and have a go at doing it, you can check the answer when you've done and when you push play. Rightio, so the oxidation, let's look at which one is gaining the electrons. Nickel is going to a 2+ ion, so nickel is losing electrons. Loss of electrons is oxidation. It also says that it's being oxidized, so that's a bit of a clue there as well. So my oxidation reaction is going from nickel in the solid to nickel in the aqueous with 2+. And it is oxidation, so it's lost the electrons, so the 2 electrons that it's lost are over there. Boom, simple. A half equation for my oxidation showing the loss of electrons of my nickel to form a nickel 2+. Then we're going to do the reduction. We were given the species being reduced was Fe3+. That's going to gain 1 electron to make an Fe2+. So Fe3+, was that in the aqueous? That sure was in the aqueous. Is going to form an Fe2+ in the aqueous. If that is going from 3+ to 2+, it needs to get 1 negative charge, so it's getting 1 lowly little electron. Let's double check everything. I've got conservation of mass, 1 nickel, 1 nickel. I've got no charge, 2+, 2 minus, no charge. Charge is balanced. I got 3+ and 1 minus. I got 2+. I've got 2+ over here. Charge is balanced. I've got 1 ion. I've got 1 ion. My mass is balanced. And just remember your electrons there, they're negligible mass. So they're just in there. So, and also the electrons that are being lost up here are the electrons that are being gained down here. So if I wanted to write an overall balanced equation, I need to make sure that my electrons are all accounted for. So I'm losing 2 electrons up here, but this equation is only gaining 1 electron. So in order for this reaction, this oxidation reaction to occur, both electrons need to go somewhere. So for every one of these reactions, we need to do 2 of these reactions down the bottom. So I can put a 2 there, I can put a 2 there, and I can put a 2 there. And then I can get my overall ionic equation. And my 2 electrons are going to just cross out there. It's like when you got the same number on both sides of an equal sign. You don't really need it there. So you got 2 electrons over there, 2 electrons over there. They're just going to cancel out with each other. Then my overall ionic equation. I've got my nickel in the solid plus 2 Fe3+ in the aqueous. And I am forming nickel in the 2+ in the aqueous and 2 Fe2+ in the aqueous. Let's double check that. If we go back and make sure that everything's conserved, then it's hard to get it wrong. I've got 1 nickel going to 1 nickel, 2 ions going to 2 ions. My overall charge on this side is 0 and 3 plus. So I've got a 3 plus charge over here. Over here I've got 2 plus. Oh, no, that is not right. I've got 2 lots of 3 plus, don't I? So I've got 0 and 6 plus. So I've got 6 plus over here. I've got 2 times 2, which is 4 plus, plus 2 plus. My charge is conserved. Remember, the charge doesn't have to be neutral on both sides, but the charge does have to be the same on both sides. If I go back to my slides and click, hopefully that is the correct answer. Nickel solid plus 2 Fe3 plus goes to Ni2 plus aqueous plus 2 Fe2 plus aqueous. You beauty. Let's do another one that's a little bit trickier. Construct a balanced ionic equation from the following half equations. This time I'm given 2 half equations and I've got to combine them into a full equation. In fact, we won't do this on the board. We'll just talk through. If you want to pause and maybe have a go yourself, then you can do that. Otherwise, resume here. Let's have a look. We've got 10 electrons that are being gained in the reduction reaction, and we've got 2 electrons that have been lost in the oxidation reaction. So what that means is that we would need to make the number of electrons on the left-hand side be the same as the number of electrons on the right-hand side. And I can do that by finding the lowest common multiple between each of these, and that would be 10. If I multiply this whole equation by 5, that would give me 10 electrons. These 2 10 electrons would cancel out, and then I could very easily just combine the 2 things where I'm going to have 2 IO3 minus, and I'm going to have my 12H plus, but then I've multiplied this bottom equation by 5, so I'm going to have 5 ZNs there. And on this side, I'm going to have I2, 6H2O, but then I multiplied the bottom equation by 5, so I'm going to have my 5Zn2 plus there. All my electrons have cancelled out. Excellent. That's the first part of this lesson done. Let's keep going into this second part of the lesson. We're going to look at these things called oxidation states, also go by the name oxidation numbers. And these are just numbers that very quickly tell you, well, the state of oxidation it's in, essentially how many electrons it's gained or lost in the current form that it's in. What do I mean by that? Oxidation state or oxidation number, I'm going to use those 2 terms very interchangeably. It's a number given to an atom in a compound that describes how oxidized or reduced it is. So essentially it's just the number of electrons that that atom has gained or lost. It can be positive, it can be negative, or it can be 0, and you need to include the sign if it is a number. Possible for atoms to have a number of oxidation states, and you can see those on the periodic table. If you look at the periodic table, you often see little charges down in the box, and for example, it might go like 2 plus, 3 plus, 5 plus, you know, there might be 3 oxidation states that element can be in, or it could be, if you look at hydrogen plus 1 minus 1, there can be 2 oxidation states, but a lot of periodic tables will just show you the oxidation states they can exist in. How do we know what oxidation state they exist in? We have certain rules. Rules. We like a good rule. Rules for determining oxidation number. All right, first rule, the oxidation state for uncombined elements is 0. So if you just have an element like a neon or a hydrogen gas or a copper, those are just 0. If it's uncombined with anything else, it's just a 0 oxidation state. Pretty easy. This one's also easy. The oxidation number of a simple ion is just the same as its charge. For example, sodium chloride. If I have a sodium chloride ionic compound, I know that sodium is an Na+, I know that chlorine is a Cl-, because that's in group 1, that's in group 7. So the oxidation number of my sodium is +1. The oxidation state of my chloride is -1. It's just the simple ion that it exists in. If I've got AlCl3, I'll use my blue pen, AlCl3, same thing. Aluminium is going to be +3 because that's the ion it makes. Chloride is going to be -1. The oxidation number of a simple ion is the same as its charge. This third part, this is where it gets not trickier, but here's just where there's a few extra rules that we need to be able to recall. But a lot of them just make sense with what we already know about the chemistry of certain elements. So there's nothing too radical in there. If we have compounds, such as molecules, certain atoms have fixed oxidation states. So these are the rules that we can use to determine essentially the oxidation state of any atom in a compound. If we have a group 1 or a group 2 element, it is always going to have an oxidation state of +1 or +2. That's because those ones just make those ions because they just have that 1 or 2 electrons in its outer shell. And I mean, like a group 1, if it was to gain 7 electrons, that's just very unfeasible. Our group 2, if it was to lose just 1 electron, well, that would make it even more reactive, so it's going to lose 2 electrons. So group 1 and 2 always form +1 and +2. Fluorine will always make a -1. Fluorine is our big boss of electronegativity, so it's always going to make a -1 no matter what it is bonded to. There are no exceptions to these rules, and we're going to see how to apply these rules in just a second. The two other rules. Hydrogen is usually a +1. The only time is when it is a -1, when it's in the hydride. For example, if it is in a compound with a group 1, because the group 1 is always going to be +1, so if we have KH, it means it has to be -1. So hydrogen can be +1 or -1 in the hydride. Oxygen is usually -2, except when it's in a peroxide, for example, H2O2, because our hydrogen is going to be +1 in that situation. And it's going to be +2 in F2O because our fluorine is always -1 and that's neutral. All right, I went through them very quickly. Let me explain that in a bit more depth by going through some examples. So we can use these rules, and we can also use the overall charge of the species to determine the individual oxidation numbers of each atom. Let's do a bunch of examples. If you think you can jump ahead and have a go, by all means do that now, and you can check your answers afterwards. We are trying to determine the oxidation number for each of the atoms in bold. All right, my first one is K2O2. All right, let's have a look what we've got. We've got potassium, which is in group 1, oxygen, which is in group 6. If I look at my rules, group 1 is always +1 with no exceptions. What does that mean? That means that my potassium is going to be a +1 because there's no exceptions to that rule because it's in group 1. Now, this species is a neutral species, so this has an overall charge of 0. Yeah? So it becomes a little bit of just very simple algebra type questions. If I've got 2 lots of +1, because I've got 2 potassiums, and I've got 2 lots of my oxygen, what does my oxygen have to be in order for this to equal 0? Because this is a neutral compound, this has no charge. So 2 times 1 is +2. So this O2 has to equal -2. So if I got 2 of them, it means this has to be -1 because +2 minus 2 equals 0. So my oxygen is going to be -1 in this situation. Don't worry if that didn't make too much sense. Hopefully as we keep doing these next 5 examples, it will begin to become a bit more clear. Let's have a look at another one, P2O5. Number 2, P2O5. Now this is a neutral compound. There is no charge on this, so it's going to equal 0. All of these oxidation states added together is going to equal 0 because we have no charge on this compound. What do we have? We've got a phosphorus and an oxygen. Well, we do have a rule for oxygen. We don't have a rule for phosphorus. Oxygen will be -2. It won't be any of these because we're not in these situations. So in this case, our oxygen is going to be -2, right? But we have 5 of them. So that means -2 times 5 is -10. What do I have to add to -10 to get to 0? Well, I have to add +10. +10 minus 10 is going to equal 0. I've got 2 of these phosphorus. That means that one of these phosphorus to make it +10 is going to be +5. So our phosphorus is going to be +5. Very, very simple algebra. No tricks about it. So P2O5, my phosphorus will be +5. What about this nasty looking compound that I don't even know what it's called, but I'll write it out anyway. Am I going to run out of space? I'm not going to run out of space. I have HASO42-. This is a little bit of a different situation. This time, I don't have a neutral compound. I've got a charged compound. So that means when I add up all the oxidation states, it's going to give me the same as the charge. This all has to equal -2. I've got an oxygen, I've got a hydrogen. If I look back at my rules, there's no rules for AS, which I think is arsenic, but we do have a hydrogen, we do have an oxygen. We've got some exceptions, but that's none of the exceptions in this situation. So they're simply going to be what they normally are. So that's going to be a +1. That's going to be a -2. Now, I've got 4 lots of -2, so that's going to be -8. I've got just 1 + 1, so that's going to be +1. So +1 and then something for the arsenic, -8 equals -2. Well, if this is a +1 there, if I go -8 + 1, I get -7. To get -7 up to -2, I have to +5 to that. So my arsenic is going to be a +5 oxidation state. We can double check that. 1 + 5 is 6, -8 is -2, so my arsenic has to be, I hope that's arsenic, I keep saying it's arsenic. I don't know what else it'd be, pretty sure it is. This will equal +5 for the arsenic, pardon me, just having a sip. All right, 3 more to finish off the lesson. If you didn't have a go before, but you think you've got the hang of it now, it might be a good idea to pause and give it a go now. Otherwise, we'll just power on through. Change my colors because my black marker's getting a bit shaky there. All right, number 4, I've got sodium SO3 like that. We want to know what the sulfur is. Our sodium is always +1. Our oxygen in this situation is -2 because it's none of the exceptions. We have a neutral compound, so this has to equal 0. There's no charge on this compound. I got 2 lots of sodium, so that's going to be +2. I got 3 lots of oxygen, so that's going to be -6. +2 - 6 equals 0, so that's going to give us +2 - 4. +2 - 6 is -4, so our sulfur has to be +4 in order for that to equal 0. So +4 for the sulfur. 6 - 6 is equal to 0. Let's double check that. We get +4. Excellent. NH3, 2 more to finish off. NH3. My hydrogen is +1. We've got a neutral charge, so we've got to have it equal 0. We've got 3 lots of +1. It's going to be +3. So my nitrogen has to be -3, 4. I'll circle the ones that are the answers. -3 for nitrogen in order for that to equal 0, because it's a neutral compound. And the last one, which is ClO2- for number 6. ClO2-. So we've got a minus charge, so we've got to have this whole thing equal -1 because it's a charged ion. We have an oxygen, however, this isn't any of the exceptions, so that's going to be -2. If I got 2 lots of -2, I got -4. In order to have -4 equal -1, I've got a +3 to it, so my chlorine here will be in a +3 oxidation state. If I go over here and I check that, we get that. Excellent. We're going to use oxidation numbers in the next lesson a fair bit, so there'll be a bit of a recap there if you still feel a bit shifty on it. But it's just sort of simple algebra, a few simple rules you need to remember, and you can work out the oxidation state very easily for any atom in any sort of compound. And with that, we finish the lesson. What have we done? We have calculated oxidation numbers of elements in compounds and ions, described and explained redox processes in terms of electron transfer and changes in oxidation number. The tasks, if you would like to consolidate your understanding of what we've looked at in this video, pause now, work through the columns one at a time, starting from the bottom and working your way up. Excellent. Thank you so much for your time. I will see you on the second lesson on our Unit 6 into electrochemistry. Have a fab day. See you later.